Okay, let's check out some normal density functions and really quick background. What the heck is a normal density function? Well, the ugly explanation is the function fits this model to the right here. Okay, all of this, but this could be, the most hideous looking section, and come to find out, probably one of the easiest things, in my opinion, especially if you've already taken a statistics course. Now, even though that function is hideous, look at our expected value, e of x. This kind of looks like a cursive u or m. It's a Greek variable. It's called mu, mu. Okay, I'll try to write one kind of clean, but you should have seen it before. The one symbol for this is like average. Okay, so it looks kind of like that, right? Mu. And observing that formula up there, that function, wherever mu is, that is your expected value. The variance is your sigma, but squared, and therefore standard deviation is sigma. Now, if you have taken stats before, like, oh, I think I've seen this, a normal curve, right? That just means a bell curve. And in particular, if the mean, if the expected value is 0, okay, right there, right, is 0, and the standard deviation is 1, the sigma is 1 right there and right here, then it falls under the standard normal curve, and we could use a z-score, and we'll look at that in this example here. But the z, right, if mu is 0 and standard deviation is 1, anyways, the z-score x minus mu over sigma is right there. So I probably should have wrote that. We won't need it until we get to this example, but a z-score, to use this table here in a minute, is x minus mu, x minus the mean or the expected value over the standard deviation over sigma. Okay, but first, let's look at this hideous problem here, this f of x, 1 over 5 square root of 2 pi e to the negative 1/2 x minus 3 over 5 squared. Okay, it wants the expected value and the standard deviation. So our expected value is mu. And observing this, the mu here is just right there, right? It's 3, x minus 3. This thing fits exactly in that form to the right. So the mu is 3, the expected value is 3. Okay, and the standard deviation is just sigma, and we could see right here, right, that there's sigma, and also here's sigma, which are the same, which is great, otherwise it doesn't even fit this normal density function standard, right? So the standard deviation is 5, which means this isn't a normal random variable. Shouldn't have probably said normal. Oh, sorry. Yeah, it is normal. It's not a standard normal. Okay, the standard is when the mu is 0. Standard deviation is 1. I apologize. Brain fart. Okay, moving forward. That's it. Okay, that's all we had to do. If you're given that, look at the formulas, find your mu and sigma. This, I didn't state that. I don't think that Greek letter is sigma there, mu and sigma, and you have your expected value and your standard deviation. All right. So next, you will have this table, and it's talking about the area under the standard normal curve. So why? Because looking at that function, I don't want to integrate that, right? That thing looks hideous. So we have this table here, and to explain this table, what they're saying is it's symmetric. The standard normal curve, which means the standard deviation is 1, and the mean right here is 0. Okay, and it's symmetric. So it's saying if you start at 0, the area under the curve to the right, where z is any of these values, is equivalent to all of the values in the table. So at 0.00, we know like it should be 0, right? But as you start moving 0.01, we get this area. 0.02, we get this area, and so forth. This will make much more sense with some examples. Now, what it does not give is the area to the left of the curve, like the negatives. However, we know that it's symmetric. So, if I had example A here, if I had probability of 0 to 1.3, that's equivalent to this 0 or negative 1.3 to 0. Okay. Now, different books, different authors use different notation. I believe, this textbook, and it's pretty common, I guess, to say this area here from negative 1.3. So I'm picturing, z is negative 1.3 up to 0. Well, that's going to be equivalent to going 0 to 1.3. Okay. So what we say is the area of 1.3. So then I look in this table, I'll use a highlighter here, and 1.3, and I don't have a second decimal place, so we get that 0.4032. Okay, that is the probability, negative 1.3 to 0, that z falls in that range. All right, z is greater than 0.25 for this next one. So let me go ahead and erase this purple stuff here. Okay, so greater than 0.25, we'll pretend this is 0.25, and I'm talking about all that area. Well, the table again gives the area to the left, right? So it's going to give me this area if I did area of 0.25. It's going to give me that area. So what we can do is subtract, right? So let me go and erase that. It's not area 0.25. I'm saying when we use area 0.25 right here, it's going to give me this. So the trick around that is this. First off, I know the area under the total curve is 1 because the probability of everything, right, is 1. Take away, now if I need to take away 0.5 because I need to subtract this whole left side, right? Both sides are 0.5. So let's subtract the 0.5, and I need to take away that area of 0.25, right? Next, I'm going to take away this stuff, and then that would leave me with what's left. So 1 minus 0.5 is 0.5, subtract that 0.0987, and we get, 0.4013? Yeah, 0.4013. Okay. Next example. So from negative 1 to 2.5. So now I'm going like somewhere over here to somewhere over here. So I have some negative and some positive. Well, that negative part would be just equivalent to going the positive part of 1, right? Plus the 2.5 is just going to be the area 2.5. So because the negative is equivalent to the positive, this, I'm just taking the positive A1, adding it to that, which is quite normal. Okay, highlighter, A of 1 is here, A of 2.5 is here, so we get 0.3413 plus 0.4938, right, which is 0.8351. All right, last one, probability z is less than or equal to 2. So again, 2 is somewhere over here, and we're taking that whole thing, less than or equal to 2. So, because we have the whole left side, that's 0.5, right? And then just take the area, this, wherever 2 lands. So the area of 2, so we get this number here. So 0.5 plus 0.4772 is 0.9772. Alrighty, so that's how you use that table. We're going to come right back to that once we wrap up this last example. So those were given z-scores. Okay, this normal distribution in life of a tire. So first off, it tells us it's normal. Okay. So part A, change colors here. We want the probability that'll last between 28,000 and 30,000 miles. Okay. But since it's normal, I want to use that z-score table. I need to convert these to z-scores first. It tells me the mean, E of x, and it tells me standard deviation, sigma, 2000. So we just plug these values straight into this z-score. Okay, so for 28,000, that z-score is going to be 28,000, subtract 25,000, divided by 2,000. So, I don't know why I wrote 20, just 2. So 3,000 divided by 2,000, or 3 over 2, is 1.5. So I know that for the z-scores, it's between 1.5. Now I need to do the other z-score for 30, right? So the z-score for 30. Oh, and often a notation, like they'll write z, I'm not going to write 28,000, but z28, and z sub 30 to show like what z-score you were finding. So now it's 30,000 minus 25,000 over 2,000. That's 5,000 over 2,000, or 5 over 2, which is 2.5. Okay, so part A is equivalent to asking that. So between 1.5 and 2.5. Now before I scroll over the table, if I had this, bad picture, but you know the curve, between two numbers, right, that's going to be equivalent to taking the 2.5, all of this, and subtracting out the 1.5, which would be that. Right, so this is equivalent to the area of 2.5 minus the area of 1.5. So looking at that table right here and here, we have 0.4938, subtract 0.4032, and you get what do you get? 0.4938. Oops, do something different. I was looking at the highlight one, 0.332. My notes weren't lining up. 0.4332. So 0.606. Okay, that's the probability they'll last between that. Part B, find the probability they'll last more than 29,000 miles. Okay, B, probability that x will be greater or equal to 29,000. Okay, so now I need the z-score for 29,000. Right, same process. So I know it's 29,000 minus 25,000, which is going to be 4,000 over 2,000, which is 2. So z is greater than 2, probability that z is greater or equal to 2 which is equivalent to, I'm going too far to the right, 1 minus the 0.5 minus the area of 2. That's similar to part B that we did up there. So 0.5 minus area of 2, which we get 0.4772. Oops, 772. And so you get 0.0278. No, 0.228. 0.0228. Okay, if we wanted percents, change them, but usually with z-scores and probability, we leave it like that. So about a 2% chance those tires will last more than 29,000 miles.